Good morning everyone. My name is Gunda Shiva Krishna. I am from Institute of Aeronautical Engineering, Hyderabad. We are discussing about the aerospace structural dynamics, which is under the topics of multiple degrees of freedom. So we are here to give the lecture about this modeling of continuous systems and which equations also. So what is meant by been already discussed, and once again we are going to discuss about this. What is meant by multi degrees of freedom? Multi degrees of freedom is nothing but if we are having the two axes x and y and z, if you are taking, okay, in this the x forces into the two directions in two varieties like variations, or else into the different axes, different axes, mass is moving into the x axis, y axis, or else into the different rotations also. It will be called as multi degrees of freedom. In single degrees of freedom we will be saying that only one forces is acting on this mass. Okay, one force is acting on the mass, we will be take it as single degrees of freedom. Now we are taking into this multiple degrees of freedom as a multi degrees of freedom as a system, and eigenvalues problems also we are going to see into this particular topics today. So here, what is meant by multiple degrees of freedom system? So as I stated that most of the engineering systems are continuous and have infinite number of degrees of freedoms. As you say that there is a piston connected to this connecting rod. Okay, if there is a movement is occur, which is top dead center, bottom dead center. Okay, if the piston is moving up and down, okay, if the piston is moving up and down, so it is connected with this x-axis. Okay, y-axis it is connected. So again it is connected to this another connecting rod. Okay, connecting rod and cylinder, piston. These are all comes under piston. So these are all systems are connected continuously, and if it is connected multiple connections, then if the motion is occurred, then it will be transferred to this one motion to another motion. Like here in this linear motion, it has been converted into this rotating motion, and rotating motion to again it will be connected to this linear motion. It will be continuous, will be going to be run. Okay, this is called as multiple degrees of freedom. So multiple degrees of system and continuous and have infinite number of degrees of freedom according to the applications. According to the application means into this piston as a one of the example, and different building blocks are cranes systems and mobiles and rockets and space systems. It will be different from the one of the system, one of the each and every systems. So in this infinite number of degrees of freedom, the vibration analysis continuous and system require a solution for this partial differential equation, which will be quite difficult. So as we know that partial differential equation PDEs are small differentiation with these differential equations, which will be concentrating on this dou only, dou by dou x or dou by dou t or dou by dou delta. Okay, like this it will be going to come because we are concentrating on a particular event like velocity or else time, temperature, okay, and density or else pressure. All these things which will be varies according to the second by second. So all these things will be going to be concentrated and calculated by using of these partial differential equations, which will be for some small difficulties will be going to be happens into the calculation multiple degrees of freedom, because it will be connected to the one system to the another system. So one system is connected means if there is a movement is occurred into the linearly, and another side it will be going to be continuous, rotation will be going to continuously, it will be connected as per connection. Okay, so to know this angle of theta, okay, or else degrees of rotation, okay, angle of rotation or else length if you are taken, then it will be comes to be into the partial differential equations point of view. So we require to be some particular event only, so that's why we are using these partial differential equations. So in fact there is a solutions do not exist that many partial differential equations. The analysis of multiple degrees of freedom on this other hand. So here it is the most of the partial differential equations will be having some analytical solutions. So analytical solution means we are having already some predefined equations already there. So with this we can able to continue for the predefined analytical solution, because we cannot able to solve at a time all the solutions. So analytical solutions we are having this predefined one. Okay, partial differentials. Okay, does not exist for many of the partial differential equations. So analysis of the multiple degrees of freedom systems, on the other hand, requires solution of set of ordinary differential equations also. So with these PDEs, we required P differential equation also. Differential equations, if there is not, then we require to be know each and every term for the differential equations as well as integrations also. So here we are following with this partial differential equations once again, and we are supported with these differential equations also. Now coming to this simplicity of this analysis, continuous systems often as approximated as a multiple degrees of freedom. So it will be taken as in multiple degrees of freedom mostly. Okay, for the system having n degrees of freedom, like as we said in the piston, and it is moving towards this connecting rod and everything, like this it is connected to the engine and it is connected to the cylinder, and like that number of connections is there. Once it is moving, means once motion it is coming here into the piston, if there is a multiple movements it is connected, or else connection is going to be happen. Like if you are taking as a clock, okay, seconds to minutes, minutes to hours, okay, like this it will be going to be connected. So 1 second if it is moved, then it will be small changes in hours and minutes also, right? So there will be a small connection will be going to be happen, right? So that will be having n degrees of freedom in each and every associated with the natural frequencies. So here is a movement will be going to come. If there is a x-axis, y-axis movement is coming, so there will be each and every natural frequency will be differ for the each and every degrees of freedom. Okay, and each will be associated with its own modes. So each and every second, or else each and every natural frequency is associated with these different types of modes only. Okay, and multiple degrees of freedom as a system. Here different method can be used for approximate continuous systems as a multiple degrees of freedom, as we said previously. Now a simple method involving the replacing the distributed mass or inertia system. So which is one of the simple example has been taken method for this. So though here we are replacing the distributed mass or else inertia to this finite element of lumped masses or else rigid bodies. Okay, so here we are having the mass 1, mass 2, if it is there, we can able to convert this into the small elements or else lumped mass systems. Lumped mass system we call. Okay, lumped mass systems we call. So it can be able to complete it as a finite element method or else by using a rigid body method. So lumped masses are assumed to be connected to this massless elastic damped members. So these are all connected to this spring systems or else elastic damped system. It will be connected, right? It will be connected to this C. Mass is connected to the C, which is undamped massless systems. So it will be taken as in considered as springs only, or else by using dash part, which is not having any masses. So massless elastic damped system which will be connected. So now linear coordinates of this used by to describe the motion of the lumped masses, such as model called as lumped parameters or lumped mass or discrete mass systems. So this is the DMS will be going to be taken as highlighted, because in this most of these terms will be going to be happening to this discrete mass systems only, or as lumped parameters of lumped masses. So we are not going to take this, mostly we are taking this DMS only, discrete mass systems only. Okay, the maximum number of coordinates necessary to describe this motion of these lumped masses or rigid bodies defined in the number of degrees of freedom. So according to the number of degrees of freedom, it will be defined as this number of coordinates. Okay, different coordinates will be having these different masses. Okay, different coordinates will be having different motions. So naturally, the larger number of mass systems in this model, the higher number of accuracy will be going to be results. So if you are having the y, x, z, so different coordinates we are having this, and different masses systems we are having, then accuracy will be going to be increases for these discrete mass models. Okay, so here it is the one of the example as multi degrees of freedom as a M3, M1, M1, M2. So here it is the each floor we are considering as masses. Each floor is considering as a masses. So each and every floor is concentrated with this number of items. Like in the balcony, we are having fridge, ACs, TVs, and some what are the balconies is there, whatever the items we have kept, this will become to this masses. Okay, all this mass will become to be concentrated at the single mass concentrated center, and these pillars are taken into the terms of elasticity or dampers. Elasticity or dampers. As we said into this, we are written into the form of, here it is a simple arithmetic indication of a lumped parameters of model has used. So here it is the example, three-story building has been given in the figure. Automatically suggested that is the three multiple mass models are located in this figure. As this model, inertia of this system assumed to be concentrated at 3 points. Masses are located to each floor level, and elastic mass of the system are replaced by using of the springs. So here it is the springs we are replacing to this. So spring is nothing but K, K2, K3. Like this, we have been improved. Okay. So in this, once there is a force is given, okay, and there is a X movement will be going to be happen. X movement is going to be happening to this. Okay, that is nothing but with this X forces, with these forces into this horizontally. So building, three-story building may be moved towards some forces deflection. So another popular method for this, most of the continuous systems or multiple degrees of freedom, involves with the replacing geometry of a system by large number of small elements. So that is nothing but we are dividing each area into these small atoms. Okay, small atoms we are dividing. That is nothing but we are taking into this finite element modeling. Okay, finite element modeling or methods we are going to take, and this is nothing but equilibrium conditions will be taken. This is assumed to be a simple solution into the written elements. So principles of compatibility and equilibrium are used to find the approximate solution to original solution systems. This is nothing but we call it as a finite element methods. Okay, finite element methods we call. Okay. So into this Newton's second law equation derived from this equation of motion will be taken. How it will be said that it can be adapted that to derive equation of motion of the multiple degrees of freedom system using second law of motion. It is said that setup of suitable coordinates to describe the position of various parts of the masses and rigid bodies in the system. So we require to be make that each and every coordinate into the each and every position, and properly we have been given in the rigid body system. So in rigid body system, if there is a mass is distributed towards right side and center or left side, whatever it may be, we require to be make it as in the according to the coordinate. According to the coordinate, we require to be placed into this model. Okay, assume that suitable positive directions of the displacement and velocities, acceleration of masses of these bodies will be going to come. So if there is a okay, in this floor we are having the sofa and TV as well as some chairs, and here it is the some washing machine if you say this. So in this all these masses will be going to be concentrated, and if there is a body deflected, if there is a large weight is comes, and all these masses are distributed weights should be comes into the positive directions only, the suitable positive directions of these displacements. So it will be going to be concentrated on this floor, will be going to be have like this. Okay, displacement should not be having that opposite direction. Okay, displacement should be under the positive directions only, must be taken as is. Okay, determine the static equilibrium configuration as a system and measure the displacement and of the masses rigid body system from their respective static equilibrium position. Determine the static equilibrium here. So static equilibrium means here we are having this, how much weight it is having, and how much equilibrium it is going to be make it, because of this under the floor and above the floor, below the floor, it will be reaction forces also will be going to be make it, right? Reaction forces also we need to be make it measure, and then it will becomes under the static equilibrium. Once if there is a forces is giving towards upwards, then we should be given a respect to reaction force also, then it will be going to be comes under the static position. Otherwise it will be going to be movement position will be going to come, right? We should not be given any movement into the like in the desk or a sofa. If we are having continuous movements, will not be going to be sustained into this building. So we are giving as one of the static motion into the static system we are giving. Okay, static equilibrium of the configuration of the system, and measure the displacement of the masses and rigid bodies from their respective static equilibrium position. So if you are giving as a into the screen, if you are saying that if you are clicking on this directly, okay, if you are giving the particular different masses into the sides of the windows or else sides of the panel, so it will be giving some input, so it will be having some curvature out there, and it should be in a positive way, and each and every side there will be reaction is going to be happen, that will be comes under this static equilibrium, and it will be measure displacement and rigid bodies from their respective equilibrium position. So how much displacement is going to be occurred, so we should be given a respect to how much it is, like 100 kgs if it is there, with this 100 kgs how much deflection is coming, how much displacement is coming, we should be make that into the respective static equilibrium positions, and draw the free body diagram of each mass or rigid body system, and indicate the spring damper system, external forces acting on the each mass system or rigid body system, positive displacement or else velocity given into the mass rigid body system. So each and every time we require free body diagram, and we require to be maintained all these mass, how much force is there, how much reaction force is there, all these things we need to be noted down, and we require to be find this velocity or else displacement or else mass rigid body, how much it is displacement is came, we require to be noted down, okay, and apply the second Newton's law. We need to be applied on this rigid body as shown in the figure. So here it is the m dot xx, so here it is nothing but F equals to ma is a second Newton's law, right? So a is here m into x double dot we have been taken, so m into x double dot is nothing but simply we are taking as a ma. The force is nothing but here we are taking I into j, okay, I into j. So here j equals to, here is the m of I equals to, we are taking mass equals to mass of I we have been taken, okay. So deriving solution from this, so all the systems we are having this m1 m2 m1, again we are having the mj and mn up to the mj and mn, like number of systems are connected, like 1 to n connected, okay, which is having the k1 k2 k3 kn kj kn, okay, number of connections are there like this. We have been explained like a piston is valve is connected to the cylinder, and cylinder is connected to the engine connected to this valve, and the rotating system and chain, as well as in the bike like a tire, it will be going to be happen, right? So each and every system we have been maintained here up to the end parts, okay. Each and every part we are having the concentrated spring system and damper system, and mass systems also we are having. So F1, F2, F3 is nothing but forces acting on these particular systems. So at this point 1, point 2, point 3 up to the point n, we are having some small motions into these elements. So each one we are taking into the consideration as summation, we are taking as a x of I into velocities and acceleration we have taken. X is nothing but distance, and I dot is nothing but velocity, and I double dot is nothing but acceleration we are having. So into this concentrated masses and summation we are having, it is nothing but free body diagram. Into this free body diagram we are having the m of I we have been taken just as a simple indicator, all the masses we are taking into the cumulative. So here we are having this k and I, we are having the accelerations, velocities we are having. Into this k we are having the xi minus of x minus y. Okay, same as it is into the damper also, xi minus 1 we are having like this. So into this k I plus 1, c k plus c I of 1 we are having. So this is nothing but cumulative, all these cumulative we are having, cumulative forces into this free body diagram we are having. So by using of the second law, what we have, draw the free body diagram of a mass system applying Newton's second law of motion, coordinate describing the positions of the masses as the x of I of t, xi of t, which is time to time respective, are measured from their respective static equilibrium equations as indicated in this figure, previous figure, and applications of Newton's second law of motion will be given as m of x double dot, that is m into a we have been taken, and forces we are connecting continuously into this k of 1, ki plus 1, k plus 2, like this, whatever the forces is having up to the n to the minus 1, up to the n we are taking. So m1 and m2 we are having taken into this period, or else we are taking into this m, c and k, like this we are having taken. So all the system we are taking into the a equals to 1, x equals to 0, n equals to I equals to 1, and with this, along with this, x to this n plus 1, x to n plus 1 equals to 0. So up to this we have been taken respectively. So which will be going to given as a forces into the cumulative system into this one direction, force, acceleration, velocity we have been taken into the same system. So we are all these masses or systems have been taken into this some simple matrices, because we can able to calculate simple equation into this matrices form, we can able to achieve very easily. Otherwise it will be going to be a very long equation, otherwise it will be going to be some mismatching into this equation also. So for this, to avoid the confusion, we are going to give into this form of matrices form: M matrices, C matrices, K matrices with the acceleration, velocity and distances. Okay, which will be comes under these forces. So what will be C, K and M, we are already know that, and matrices form into this. All the diagonals will be all the diagonal elements we have been taken. All the diagonal elements are taken as M, and all these diagonal elements we have been taken into this lumped C minus 1 plus 1, C minus 2. Like this we have been taken. Same as it is in the K. Same as it is in the K. All the diagonal elements we have been taken into this minus K into the n plus 1 have been taken into this last. So what we are going to get, all these displacement, velocity, acceleration of the velocity is given by this into this x bar, x1 forces we have been taken. X bar, x dot bar and x double dot bar we have been taken. If we goes to here, we have been taken into this vertical rows. Okay, rows only we have been taken. So now we just formulating equation simply from this equation. So from this previous equation, like this, these equations we are going to give into this system as a m double dot of mass, sorry, m into x double dot of x and k into x bar equals to f naught, f bar. So it will be going to be k. C is simply we have been taken as outside because there is a small displacement only. So small displacement we are not going to be neglected. So in differential equations of the spring mass system considered as example can be seen into the couple, and each equation involves more than one coordinates. This means the equation cannot be solved individually at the time. So in this we can able to see there is the spring mass system is connected. Spring mass system is connected. So we cannot able to achieve into the single equations. So we need to be solved with this individually at a time. Okay, at a time we cannot able to solve. So in addition to the system can be statistically coupled in since the stiffness are coupled with this stiffness matrices at least 1 0. Okay, at least 1 0 and non-zero digital form, diagonal form. So on the other hand, so if there is a matrices in the left each of this diagonal term 0 and the system said to be dynamically coupled. So as we know that there is a, it is connected with the number of elements. It is connected with the number of elements means it is dynamically coupled. So further, if the both stiffness and mass systems are matrices having the non-zero diagonal elements, the system is said to be coupled both statically and dynamically. So it will be connected with this dynamically and statically, because once there is a motion it is having, then it will be connected with the dynamics. Once the stopping of this motion or transfer of motion to the other element, it will be comes under the dynamics. Okay. So we can able to take it as m into x double dot and c into x dot and k into x equal to taken as a free vibration system can be obtained. So which is single degrees of freedom, we can be assumed that there is a free vibration of this motion of the harmonic system, which will be taken into the x of t equals to, okay, x of t equals to x dot sine omega t plus phi, omega t plus phi or as theta we have been taken. So we can able to take like this, or as x of dot we have taken into the differentiation we have taken, then it will be minus omega square of x sine omega t plus theta, which will be taken as minus omega square into x, minus omega square into x we have been taken, right? So this expression will be x represent the shape of the system, x will be represent the shape of the system which does not have any changes of this amplitude, and theta is the phase angle, and third equation of this represents with this acceleration of these free forces. Okay. So since we are into this undamped systems, we'll just stop this up to this undamped systems. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.